Hello and welcome to my talk on positive scalar curvature from a concordance viewpoint. Today, I would like to talk about my PhD project, which is supervised by Thomas Schick in Göttingen and Wolfgang Steinmann in Augsburg. But before I begin, I would like to thank the organizers for giving me the opportunity to speak here. It's a great pleasure to contribute to this event. In my talk, I will study the space of positive scalar curvature metrics from a concordance viewpoint. To this end, I will construct an approximation space that encodes only concordance information within its homotopy type. This happens in the first video. In the second video, I will have a look at the index theoretical counterpart of it and will show there that the index difference factors over the approximation space. A more detailed outline of my talk is the following one. First, I will shortly explain why we are interested in positive scalar curvature and how my thesis fits into the general theme. Then we will have a look at cubical set theory. This is a tool from combinatorial topology that is used to construct topological spaces. The reason why we are using cubical sets is that the approximation space I was talking about cannot be written down in a closed form. We need to construct it, and cubical sets are the tools of our choice. In the third section, we will apply cubical set theory to positive scalar curvature to construct this approximation space, this so-called concordance set, and relate it to the original space of PSC metrics. The first three sections are the content of the first video. In the second video, we will have a look into the index theoretic counterpart and factor the index difference over the concordance space, concordance set. Okay, so let's dive directly into the motivation. Scalar curvature is, like any other curvature, geometric quantity that measures how much a geometric object, in this case a Riemannian manifold, deviates from being flat. More quantitatively, the scalar curvature is a scalar valued function that appears in the Taylor expansion of the ratio of the volume of a geodesic ball and the ball in Euclidean space. So if you take this quotient here and take a Taylor series expansion with respect to a radius epsilon around the point P, then the scalar curvature is up to dimensional constant, the coefficient in front of the second order term in the Taylor series expansion. From that, you see that if the scalar curvature is positive, that the volume of the geodesic ball grows slower than the volume of a ball in Euclidean space, at least on those small scales where the second order term dominates the higher orders. An example for a positively curved manifold is a sphere. This is the left picture here. You can actually use this formula to prove this. I will not explain it here, but leave it as an exercise to you. And the second picture there is an example where the scalar curvature of a manifold is negative at the point P. You can see this using the second formula because the boundary circle, it goes a bit up and down, and therefore it is longer than a boundary circle in the flat plane. So this suggests negatively curvature there. I should also mention that this is an example for a negatively curved metric, but maybe this manifold has positive scalar curvature. It's not a priori clear that there are manifolds that cannot carry positive scalar curvature metrics, but there are. For example, the torus is a manifold that cannot be equipped with a PSC metric. This follows from example from index theoretic methods, for example, enlargeability or higher index theory. So having a PSC metric is not a void condition. It actually restricts the topology of the underlying, the topology of the underlying topological object. Okay, but I'm not so much interested in the existence question of the PSC metric, I rather like to count them. And when I say that I would like to count them, I mean the following. I consider the set of all Riemannian metrics on a closed manifold M that have positive scalar curvature. And I can equip this set with a natural topology, the so-called Fréchet topology. And then I ask myself a question: what is the homotopy type of the space? How rich or complicated are its homotopy groups? These questions are quite difficult. In dimension 2 and 3, this is solved, because there we know that the space is either empty or contractible. But in higher dimensions, only partial results are known. But we know, and we find that the space might be non-trivial. For example, the space, there are manifolds where the space of all PSC metrics can have infinitely many path components. So in higher dimensions, there's something going on. But how do we see this? Well, if we want to know that, for example, two different metrics lie in different path components, then we need to kind of obstruct the path of PSC metrics adjoining them. Recall that obstructions against PSC metrics on manifolds are, for example, provided by the index of the Dirac operator. If a manifold has a PSC metric, then its index is 0 because the Dirac operator is invertible. And with a slight modification of this kind, we can actually cook up secondary invariants that obstruct the existence of such a path. This kind of relative or secondary version of the index is the so-called index difference. And it is, so to say, an objective function that you feed with two Riemannian metrics, G1 and G0. And the result is then an element in an abelian group, the so-called real K-theory group, which is dependent on the dimension of a manifold, either equal to 0, z over 2z, or the integers itself. And almost all produced non-trivial examples of families of PSC metrics rely, in fact, on the index difference. So this is a really important invariant. But in fact, we can discuss, we can consider the space of Riemann metrics from two different equivalence relations. First, under the equivalence relation of being isotopic, which is nothing but a different word for smooth, being smoothly homotopic to each other. So for example, two Riemannian metrics are isotopic if they lie in the same path component of the space of PSC metrics. But there's also a different equivalence relation, the so-called concordance relation. And we call two Riemannian metrics concordant if there's a concordance between them. That is, a Riemannian metric on a cylinder that has product structure near the boundary. And well, near the boundary, you get the original matrix back. And the Riemannian metric on the cylinder that joins these two metrics is called a concordant. The reason why I introduced the concordance relation is that the index difference, there are two kinds of index difference, two versions. One is due to Hitchin, the other one is due to Gromov and Lawson. And the Gromov-Lawson index difference is invariant under concordance. Well, and with that, we come to the main theorem of this talk, namely that we have a homotopy commutative diagram of the following kind. We have on the upper left corner the original space of PSC metrics on our manifold. And on the lower left corner, we have our approximation space, the so-called concordance space. And the index difference can be modeled by a continuous map into the space of, into the classifying space of real K-theory. So it's a certain topological space that is described by this representation phenomenon. Concrete model for it would be the space of all Fredholm operators. And the nice thing is that the index difference, which is the one that is due to Hitchen, under nice reinterpretation of this model of real K theory, this map factors over a concordance space, and the second factor is precisely the Gromov-Lawson version, the one this is from which we know that it's invariant on a concordance. So this is nice theory because first of all, it shows that these two index differences agree. Secondly, it shows that the index difference is as concordance invariant as possible. Yeah, because this approximation space does not see any trace of isotopy information. It's purely concordance invariant. I will explain later in the talk what this means. And this third thing I would like to emphasize is that we really have a space level description here. So we have continuous maps between topological spaces. If you want to get the classical picture back, then you just need to apply homotopy groups to that diagram, and you get then a strictly commutative diagram of groups. Yeah. But you can also apply other things to that homotopy commutative diagram, for example, homology or K-theory itself. So we have more tools at our hand with this description and maybe get new information out of it. One thing I should mention is that the result, quite similar result, was published by Johannes Ebert almost 10 years ago. He also showed these two index differences, these two notions agree, but he only showed that the composition of the left vertical map and below horizontal map agrees with the previous one. So he did not consider this kind of factorization, which gives the strongest result here. And in fact, we do not rely on his result, but can prove it directly. So we get Johannes Ebert's result back. Okay, with that, I would like to have a short look at cubical sets. As I told you, this is the construction tool we use to construct this approximation space. This is unfortunately a bit abstract, but I try to be gentle and brief. So, okay, before I give you the introduction, before I introduce you the abstract notion of the cubical set, I would like to present an example, namely how to model a topological space in a combinatorial manner. For that, we can assign to each topological space a sequence of sets of so-called singular cubes. You actually have seen this set already in your topological 1 course. These sets form the set of bases for the singular chain complex. Yeah, the singular chain complex is a group of formal sums of continuous maps from cubes to the topological space X. But instead of considering formal sums, we only consider the maps itself. These sets of singular cubes, they are not independent of each other. There are certain connecting maps relating these sets. Namely, there are the phase maps, these partial I epsilon, and what they do is they take a singular cube and restrict it to an appropriate phase. And the tuple I and epsilon parameterizes to which phase we restrict our map. So the I parameterizes the coordinate, and epsilon takes values in plus or minus 1. And so to say, if epsilon is 1, we restrict to a front phase in the I coordinate, and if epsilon is minus 1, we restrict our map F to a back phase in the I coordinate. Besides the phase maps, we also have the degeneracies. What they do is they interpret a singular n cube as a singular n plus 1 cube by extending our singular n cube constantly into the additional direction. Well, these maps satisfy certain commutation relations coming from cubical geometry. And these commutations relations are precisely what motivates the definition of the general cubical set, because this is simply an abstraction of what we have, of the example I have shown you on the previous slide. Namely, instead of taking the set of singular cubes, we just take an arbitrary set, xn, but these sequence of sets are not independent of each other. They come with the same structure maps as the set of singular cubes, namely these phase maps, I epsilon, and the degeneracy maps, I epsilon. And here, these are just maps, but we require that these maps satisfy the same commutation relations as the maps would do in the example on the previous slide. I have not written down them in a precise manner because we do not need them in this talk, but keep in mind that there are certain conditions, cubical identities that these maps need to satisfy. And well, we want to turn this into a category, so we need to also mention what the morphisms shall be, but this is quite easy. Our morphisms or cubical maps are just sequence of maps between xn and yn that commute with the connecting maps. So this is nothing surprising. And of course, this data forms a category. And the nice thing is that this category can be used to construct CW complexes. There are certain functors from the category of cubical set to the category of CW complexes, or topological spaces, if you prefer both. And what this geometric realization does, it takes your cubical set, which can be thought as a blueprint to construct a topological space, and this geometric realization constructed. So maybe, well, not maybe, you have seen this in the example of simplicial complexes. Simplicial complexes also come in two different flavors. They are either considered in an abstract way as a set of subsets. So these are the combinatorial version of the simplicial complexes, but you can also take a geometric viewpoint by just saying that there are just a collection of simplicities in some Rn which are stick together in an appropriate manner. And for cubical sets, this is the same. The category of cubical set is, so to say, the abstract viewpoint. This is the combinatorial data, and this geometric realization translates this combinatorial data into the geometric data by just gluing cubes together according to the data the connecting maps provide. And the nice thing is that cubical sets, they are able to encapture all homotopy-theoretic informations. So the category of cubical set also has a notion of homotopy, like the category of topological spaces. And if the cubical sets are good, if they satisfy a certain filling property, which I will not explain, then being homotopic is in fact an equivalence relation on the set of cubical maps, like in topological spaces. And for those sets, these functors, the geometric realization, and the singular set, they provide a bijection on the set of homotopy classes of maps. So yeah, so the upshot is that if we are only interested in homotopy-theoretic information, which we are, then we can work in both categories equally well. And for convenience reasons, we decide to work in cubical sets because this is more appropriate for our viewpoint. As I told you, the spaces we are interested in cannot be written down in a closed form, and therefore it's more convenient for us to work in cubical sets. I hope I gave you some insight why this is useful, and what you really should take away is that cubical sets are a blueprint to construct topological spaces. And if we are only interested in homotopy-theoretic information, then it doesn't matter whether we consider cubical sets or topological spaces. This is more or less a matter of which is better applicable. And in our case, cubical sets are more applicable, more reasonable to work with. Okay. Back from the abstract stuff towards geometry, we will use cubical sets to describe our space of positive scalar curvature metrics in a combinatorial manner, and then construct with the approximation space. So let us start with the translation. First, I need a small definition because I do not want to take the cubical set of singular cubes, but I want to consider a slight variant of it, which is more fitting here. And for that, I need the concept of a block map because I want to get rid of the corners of an n-dimensional cube. And I achieve that by just extending the continuous map from an n-cube constantly to Rn, independently of the normal coordinate of each face of the cube. And with that, I end up with a block map. So more intrinsically, a block map is continuous map from Rn to X that outside of a sufficiently large cube R, that map is independent of the ith coordinate for any coordinate. So this map is actually uniquely determined on the by the restriction of to some unknownly large cube R3 n. And with that concept, with this notion of block map, I'm able to give a combinatorial model for the space of positive scalar curvature metrics on the manifold M. Namely, this is the cubical set of all smooth block maps from Rn into the space of Riemannian metrics. The face maps here can again be thought just restricting to some face, but since we do not know on which R on which cube R the block map is uniquely determined, we cannot simply choose an arbitrary R, but we want to make it independent of this choice. And this is the reason why we take the limit R to infinity. Nevertheless, you should think of these face maps just as a restriction to some hypercube, maybe at infinity if you like. But and the degeneracy maps, they do not change. Yeah, it's just extending the map constantly towards the new direction. So, and it's an easy calculation to show that this is indeed a cubical set. And it's also not so hard to show that the geometric realization of this cubical set is a CW approximation of the space of PSC metrics. So there's a canonical homotopy equivalence, weak homotopy equivalence to the space of PSC metrics. Therefore, the geometric realization of that model has precisely the correct homotopy type. We can work with this cubical set instead of the original space. So this is the translation. And it seems that we have nothing done so far, but it allows us to construct the approximation space to it. And for that, I need the definition of a block metric. A block metric is a metric that, well, decomposes more and more into a product metric on some hyperplane and the Euclidean metric. So more precisely, we call a Riemannian metric on the product of M and the Euclidean space of block metric if there is a certain R such that the metric is a product metric on a affine half plane outside of R. So, and again, we require this for all coordinates, and this has the implication that more and more towards infinity, this metric decomposes more and more into a product metric. And so, for example, here the pictures, if you look at the pictures here, you have a product of M and R2. And outside a certain region, you just have a product metric of a metric on the blue affine hyperplane. and the Euclidean metric towards the Euclidean into the normal direction. And these decompositions are compatible. So for example, at the corner point, you have a product metric of a metric of M and the Euclidean metric on R2. But of course, the metric on the corner points, the metric from it can differ. It does not need to be the same metric. Yeah. So maybe if you prefer, you can also think of it differently. You can think of it as a Riemannian metric on M times a cube that has product structure near each face, compatible product structures near each face, and we use this product structure to extend this towards R to the N. This is another way to think about it. Okay, so the approximation space is modeled by the cubical set of all block metrics that have positive scalar curvature. The phase maps are again just given by restricting a Riemannian metric towards an affine hyperplane. But again, we want to get rid of the choices, so we take the limit towards infinity. And the degeneracy maps are just adding another dimension to our manifold, so that M times Rn gets N times Rn plus 1, and we extend the metric by a product metric, where we take the Euclidean metric of a missing direction. Again, you can show that this is a cubical set, that the connecting maps satisfy the cubical identities, and of course, you do not need to make you do not need to have the curvature condition to make sense out of this. So we also could have just dropped the condition that the scalar curvature is positive, and you would still get a cubical set. In this case, we just drop the plus from the description. Okay, so this is our approximation set, and well, this is a cubical set, but we would like to make sure that this is in fact a good cubical set. I was mentioning in the crash course on cubical sets, because then we can throw the entire theory of cubical sets onto it. So for example, we know that that being homotopic is an equivalence relation on the set of cubical maps with both targets is this cubical set. And another advantage is that we have a convenient description of its homotopy groups. This also follows from abstract cubical set theory. Instead of taking the geometric realization of this space and taking then the the topological homotopy groups, we could just, we have a combinatorial description for them, which are isomorphic to the classical homotopy groups of the geometric realization. And I wrote them down here in the example. So for example, from this combinatorial description of these homotopy groups, you only have for Concordance sets. You deduce that the path component of this concordance set, of this cubical set of PSC block metrics, are precisely the concordance classes of PSC metrics on M. The fundamental group is given by concordance classes of self-concordances, and the higher homotopy groups are, given by concordance classes of block metrics that agree outside some compact set with the base point and the Euclidean, plus the Euclidean metric. So this is a nice condition to have, because we have a nice description of the homotopy groups, and we see that this space is indeed only a concordance space. It only encodes concordance information. So far, so good. But of course, we would like to relate this space to the original one, and this is done by the so-called suspension map. So this is a cubical map, where the nth element of the sequence assigns to a block map of Riemannian metrics its adjoint metric on m times Rn. We have a formula in the definition here. So what it does is it just takes, so to say, this is not direct product of metrics, it's, so to say, twisted product. And these maps assemble to a cubical map from the combinatorial model of the space of PSC metrics towards the cubical set of all block metrics. But notice that I didn't drop the plus by accident. This is, in fact, unfortunately not true, that the suspension of the block map of PSC metrics has positive scalar curvature. It can happen that, so to say, the parameter of this block map runs too fast, so that the scalar curvature might be non-negative or even negative. However, one can find a cubical subset of the combinatorial space of Riemannian metrics that are sufficiently slowly parametrized, such that the restriction of the suspension towards this homotopy-equivalent cubical subset has the right target. So indeed lands into the cubical set of all PSC block metrics. The weak equivalence condition here is important so that we do not lose any information. The weak equivalence statement says that we can work with this omnious cubical subset instead of the bigger one. Okay, this finishes the first part of the talk. Let me shortly summarize what we have seen. We have constructed a comparison set, our twiddle, that only encodes concordance information within itself. And we have shown that space of PSC block metrics, approximation space, is a cubical Concordance set. This might not be so interesting at first hand, but this is important because it's the door opener to the combinatorial world. It allows us to throw the whole combinatorial machinery towards the space. For example, we get the very convenient and element-wise description of the homotopy groups, which is important later on because we want to detect non-trivial elements, and therefore description that favors elements is really nice. And we also have seen the connection towards the original space. We have constructed a comparison map, the so-called suspension map, which we needed to restrict to actually land in the right target. Okay. Well, I hope that we had at least a bit of fun, and I hope to see you next time. Bye-bye.